Hello. This week I start the somewhat dull topic of edge detection in still images. This isn't exactly image detection in the sense that it won't tell you what objects are present in the image and whereabouts, but it is the first step in many approaches to image detection, certainly in the pre-neural network days. What I'm not going to cover in this lecture is the identification of objects in an image. That's the actual artificial intelligence parts of the process. No. Edge detection is a precursor to that part and is nothing more than large numbers of routine calculations rather than anything particularly intelligent. Edge detection is exactly what it says it is. It detects where the discontinuities are in an image. These can form the edges of an object in the image or mark out the different parts within an object. I should illustrate that with a simple example. What you're looking at is a simple cuboid consisting of 3 areas of featureless, fully saturated colour. It's probably about the simplest image you can get that still contains edges of some sort. No shadows, no shading, no speckles or other noise on the image. There are 6 visible edges, 3 of which form the boundaries between the object and the black background, the other 3 being internal edges. You'll recall from last week that each pixel in that image can be represented as a mixture of a red component, a green component, and a blue component. The 3 versions of the cuboid below show the strengths of each of those 3 components for each pixel of the image. A strong component is represented by light colours, a weak component by darker ones. Of course, I've contrived the image so that all the colours are saturated, meaning that all the components are either fully on or fully off, snow white or jet black. The red face in the image appears as a red component, but not green or blue. The yellow face appears as both a red component and a green component, as the yellow pixels are formed by turning the red and green on full power. Similarly, the cyan face appears as both a green component and a blue component. Since each of these components is now a binary black versus white, it's an easy matter to detect the edges. Here's a small section of the red component blown up so we can see the individual pixels. Below that, I've taken that same segment and shifted it up 1 pixel in the left-hand diagram and left 1 pixel in the right-hand diagram. In each case, we perform an exclusive OR operation between the individual pixels of the original image and the corresponding pixels of the shifted one. The exclusive OR simply means that we keep a pixel as black only if the 2 pixels it's based on are different, 1 black, 1 white. In the case of the image shifted up, this pinpoints the sloping edge. In the case of the image shifted left, it pinpoints the vertical edge with a few traces of the sloping edge. Now you can see why we had to both shift the image horizontally and shift it vertically. Shifting horizontally picks up the vertical edges, shifting vertically picks up the horizontal edges, and they both pick up the sloping edges to a greater or lesser degree. Finally, we perform the OR operation on the values we've just produced to stitch these 2 partial results together and give the final edges discovered in the image. The final step is to combine the edges detected from the 3 components. We've seen that the 3 different components all miss some of the edges, so a further OR operation is needed. The final result is that the image has been reduced to 6 lines, the 3 edges delimiting the object from its background, and the 3 internal edges. It wouldn't have mattered if the background had been white rather than black. Pure white is a saturated mixture of all 3 coloured components, so the pixel maps on those components would have looked very different, and the edges detected by each would have been different. However, since every edge in the original image corresponds to a discontinuity of some sort, all the edges would have been picked up by one map or other. This idea of comparing one pixel with the next one down or along is the standard method of edge detection, and has been developed into a series of algorithms which are all variations of each other. I'm about to describe 3 of them, the Roberts algorithm, the Prewitt algorithm, and the Sobel algorithm, and then show how they are adapted into canny edge detection, which is probably the most widely used approach. They are all defined in terms of grayscale images, but we have just seen how it can be extended to colour images. You split the colour images into the 3 primary colours and treat each of them as though they were grayscale images. Then at the end, when you have found the edges for the red pixels, the green pixels, and the blue pixels, you use an OR operator to combine them to reveal all the edges in the original colour image. Take a look at these 2 small sections of an image, blown up to show individual pixels as squares. you can see that there is what might pass for an edge running through each of the images. The image on the left is a high contrast image, with the pixels being black on one side of the edge, white on the other. This is the strength of the gradient at that point, meaning that if you moved across the image and went over this edge, the pixel colour would suddenly change greatly, from one extreme to the other. If you were to think of the pixel colours in terms of heights rather than colours, it would be like walking across a landscape and suddenly falling off a cliff. The gradient for this edge, represented by the letter G in the academic literature, is high. The edge is steep, close to vertical, up and down the image. Alternatively, we can measure the angle that the edge makes from the vertical. That angle, usually represented by the Greek letter theta in the literature, is a low one. Compare that with the section on the right. Here there is less of a contrast, as the edge is between two shades of grey rather than black and white. This edge has a lower magnitude, a smaller value of G. Also, the edge is closer to the horizontal, which will give a high value of theta, as that angle is traditionally measured from the vertical. Now I'm going to show you the three well-known but fairly basic edge detection algorithms: Roberts, Prewitt and Sobel. In fact, as I say, they're all just variations of each other, and once you understand one of them, you've pretty much got the measure of all three. Each of the operators calculates both the strength and the angle from the vertical of the gradient at each point in the image. What you can see on the screen is the Roberts operator in its hieroglyphics form. You know us computer science nerds, we love our hieroglyphics. Now I'll explain what all that means in plain English. See that star in those two equations at the top? That's the convolution operator, and it means taking the pixels in groups of 4 of the original image, which is represented by the letter A above. Take the first bit, for example, which calculates Gx, meaning the strength of the gradient at any given point in the image horizontally across, i.e. in the x direction. For any pixel, it's grouped with the pixel above it, and the one to its right, and the one both above it and to the right, and each of them is multiplied by the corresponding value in that matrix above. These products are then summed to give the convoluted value of the pixel at that point. Yes, we badly need an example for that. OK, here's an example of a simple image, 4 pixels by 4 pixels, each of which is represented by a grayscale value in the range 0 to 255, where 0 means pitch black and 255 means totally white. We're only going to apply just this first operator to produce another array of values, this time 3 by 3, which will be the convoluted values of Gx. Here's how we do it. Take the 4 pixels in the top left corner, multiply each of them by the corresponding value in the Gx array, and add the 4 results. This gives the value in the top left corner of Gx. Of course, since the Gx array is half filled with zeros, effectively all we're doing is subtracting the southeast value in that square from the northwest one. It does mean that the value in Gx can be negative, of course. Now slide the square down 1 pixel in the image and repeat the process to get the value in the Gx array below the top left one. This is convolution, multiplying each element in the squares that we find by the corresponding elements in our special array and adding the results that we get. This also explains why the array that we end up with has 1 fewer row and 1 fewer column than the original image. Since the value calculated requires the row above and the column to the right of that pixel, we can't calculate values for the top row and rightmost column. It's like trying to get the business end of the vacuum cleaner right up to the edge of the skirting board. Can't be done. And here I've done the same thing to produce another array of values, gy, using the other convolution array. In fact, it's not the values of gx and gy that we need. The output of the Roberts edge detector is a gradient strength g and a gradient angle theta for each point in the image, minus the single row and column that we can't calculate. You might recognize these two equations as being similar to the sort of thing you would see with right-angled triangles. The strength of the gradient is like the length of the hypotenuse, and is calculated using something similar to Pythagoras' theorem. You square the x and y components of the gradient, add these squares, and square root the result. Assuming that the pixel images are based on grayscale, extending from 0 to 255 inclusive, this gives a maximum possible gradient strength of 361. The gradient angle is calculated by treating the y component as the opposite side of the triangle, and the x component as the adjacent side. and calculating the angle using the inverse tangent operation. This can give us any value from 0 degrees to 360 degrees, depending on which side of the gradient is lighter and which is darker. You might also remember that the two arrays used to calculate the components gx and gy were essentially diagonal ones. Gx compared the northwest corner with the southeast, gy compared the northeast corner with the southwest. Clearly, these will give a high gradient angles for edges that correspond to diagonal lines. However, we find it more instinctive to work with simple points of the compass, so there is an additional part of the equation that subtracts 135 degrees in order that a gradient angle of 0 actually corresponds with a vertical edge that is lighter on its right-hand side and darker on its left-hand side. 135 degrees is 3/4 of pi for all those hoity-toity mathematicians who prefer their angles in radians, but I'm a straightforward feet and inches kind of guy who's perfectly happy with degrees, thank you very much. And that's what the Roberts edge detection algorithm produces, an array of g values, an array of theta values. In practice, we wouldn't store all the gx and gy values in arrays of their own. The moment these components were calculated, we would turn them into g and theta values and jettison the components before moving on to the next pixel. I've taken the liberty of copying this image from the Wikipedia page describing the Roberts algorithm, showing a bicycle chained to a bike rack in front of a brick wall. On the left, you can see the original grayscale image, and on the right, the result of Roberts edge detection. High gradient values are represented by light colours, and low ones by darker colours. On a simple diagram like this, we can't display the gradient angles, of course, but they will be available to any program that had to analyse this image further. It isn't immediately obvious looking at it, but the processed image is 1 pixel narrower than the original in each direction. You'll notice that what Roberts does not do is specify the meanings of the parts of images. It does not say, this pixel is part of the edge of a bicycle, or even, this pixel is part of a curved edge. The resulting data will be passed to something like a neural network, which would do that sort of thing. Here's the second of the edge detection algorithms, developed by Judith Prewitt in 1970. It's similar to Roberts, except that the two convolution matrices to determine the gradients in the x and y direction are now both 3x3 matrices, each applied to 3x3 groups of pixels in the image to produce the convoluted value corresponding to the central number. This means that you lose 2 rows of pixels, one at the top of the image, one at the bottom, and 2 columns of pixels, one on the far left and one on the far right. You can see that the two convolution matrices are basically transposed versions of each other, designed to compare a short line of pixels on one side of the central point with a matching line on the other side. The GX matrix, for example, compares the line of pixels above the central point with that below it. Although it might look as though the values in the matrices have been written wrongly, with rows mistakenly swapped for columns and vice versa, they are correct. They're written like this because of the way matrix multiplication is carried out, with the rows of the first matrix being combined with the columns of the second one, the A matrix in this case. Unlike for Roberts' edge detection, the two convolution matrices are not diagonal, which means there is no need to add or subtract any angle to or from theta in order to stick to the principle that 0 degrees represents a vertical edge. And here is Sobel edge detection. The only difference between this and Prewitt is the makeup of the convolution matrices, so I haven't even bothered putting in the rest of it. Do I need to go into details? I don't think so. One thing I will point out is that the signs on the numbers in the arrays are actually swapped, plus becoming minus and vice versa. Wind the video back a few seconds and take a look. So the Sobel operator produces a gradient angle of 0 degrees for vertical edges which are darker on the right-hand side rather than lighter. Indeed, there's nothing special about any of these 3 edge detection algorithms. They are all very much of a muchness, and there's nothing to stop you producing your own convolution matrices in a similar way. However, their efficiency is improved by incorporating them into a larger procedure developed by John F. Canny in 1986. Here's the Canny edge detection algorithm, and you can see that it is basically one of the 3 algorithms you have already seen with Go Faster Stripes. Firstly, we reduce as much noise in the image as possible to prevent it from triggering spurious edges. Secondly, we use one of the 3 algorithms we've met so far, Roberts, Prewitt or Sobel, or something of your own devising. Hey, it's your program. to perform the actual edge detection. This gives us a series of potential edges and angles. After this, we have to whittle away at those possible edges to leave just the genuine ones. The third step is to remove any edges that aren't the maximum of their surrounding pixels in order to sharpen the edges. The potential edges that are left are then categorized as either strong candidates or weak candidates using a double threshold. Finally, we promote weak edge candidates to strong ones if they are attached to strong edges. Any potential edge that makes it through all those steps has achieved genuine edge status and appears as a white spot on the final result. So, here's each step described in turn. The first step is noise reduction. Noise is defined as any part of the signal that is not actual information. In edge detection terms, noise is any part of the image that is not an edge. Here's a small part of that grayscale image of the bike racks in front of the brick wall. Enlarging it shows that the brickwork has a grainy texture. However, from an edge detection perspective, that's simply noise, which might lead to some spurious edges appearing. This is the bell curve, also known as a Gaussian curve. I dare say you recognise the two-dimensional version. On the right, you can see a three-dimensional version of the same thing. Below that, the 3D Gaussian curve has been flattened into a two-dimensional matrix, with the central square of the matrix representing the peak of the curve. Make a rough comparison between the values in the matrix and the heights of the points in the 3D curve. This matrix is going to be used to reduce the noise in the image. The matrix is convoluted with the individual pixels of the image in the same way as we've seen before. Multiply each element in the Gaussian matrix by the individual pixel values and add the result. We are trying to average out irrelevant differences between pixels while keeping relevant ones, so we have to scale it down. The sum that we get is divided by 159, which is the total of all those values in the Gaussian matrix. This gives the convoluted value for the central pixel in the 5x5 section of the image under consideration. In the example shown on screen, we get the smooth value for the pixel ringed, originally 4, which comes out as 1.84. This is the first convolution operation that we've done that couldn't be performed entirely in integer arithmetic. However, if we wanted a rounded value, 2 in this case, then it could be easily achieved using integer division at the end. Step 2 is to apply an actual edge detection algorithm to the noise-filtered image. This is where you fall back on your algorithm of choice. We've been through 3. One thing I should mention is that for each pixel in the image, the gradient angle is limited to one of 4 values. 0 degrees for a north-south edge, regardless of which side is darker, 45 degrees for edges running vaguely northeast to southwest, 90 degrees for roughly horizontal edges, and 135 degrees for northwest to southeast edges. Other gradient angles are rounded to these values. The next step is to remove any potential edges that are not higher than both the pixels on each side of them. This makes the edge thinner and therefore sharper, like whittling a knife blade to a fine edge. Take a look at these pixels. There's a horizontal edge running through this image, but it's a thick and fuzzy one. Using just the edge detection that we've met so far, all those pixels that aren't black are labelled as a potential edge. Take a vertical slice down through that image. Only one of the gradient values is larger than both the values above it and below it, the white square labelled 250. This is a maximum, a peak which we take to represent the true position of the edge. It will be the same if the thick fuzzy edge were vertical or vaguely diagonal, except each gradient value will be compared to either the ones to its right and its left, or to the ones along the appropriate diagonal. It all depends on the gradient angle of the gradient being compared. Only the gradient values which are higher than both their nearer competitors are kept, and all potential edges are reduced to a thickness of 1 pixel. Almost there, only 2 more steps to go through. Even after this massacre of the gradient values, there are still a few that have gotten through in spite of the fact they don't actually represent true edges. We take each surviving gradient edge and compare it to 2 thresholds, one higher, one lower. Any gradient that is the higher threshold or above, that's a strong candidate. Any gradient value that's between the 2 thresholds, that's a weak candidate. It could still represent an edge pixel, but it's on probation. If a value is at the lower threshold or below, it causes the gradient value to be suppressed. It falls at this hurdle. The question is, of course, how to set the thresholds. There's a great deal of latitude as to this, but one common approach is to take the highest gradient value in the entire image and set the lower threshold at 1/3 of that and the upper threshold at 2/3. The final stage is to assess the weak edge candidates to decide whether they are to be promoted to strong candidates or rejected altogether. Any weak candidate for an edge, such as the central grey values shown in these 3 examples, are compared to the 8 surrounding squares. If at least one of them contains a strong edge candidate, then the weak candidate is kept and assumed to be an extension of that strong edge. If there are no strong edge candidates in those surrounding squares, then the weak edge candidate is removed. So there you are. The Canny edge detector is long and complicated and has made this video run a little over time. As you can see, it's very strict and, in my opinion, not always an improvement on the 3 much simpler methods that you met what seems like an age ago. Here's another example, also from the Wikipedia page, showing a model steam engine. Compare the edge detection produced by the Sobel algorithm with the result of applying the Canny edge detector using Sobel in step 2. Canny has indeed removed the vast majority of the noise in the image, but it has also missed several important edges, to the point where something like a neural network, handed that result, might well have difficulty identifying the various components of that engine. I think that's a good point to end the video. I'm sorry it's been so long, a little too much material for a normal length talk, but not quite enough for 2 of them. Next week, I shall show how these principles can be put into practice in a JavaScript program. Goodbye.